Learning Outcome 1-3. Determine memory, causality, stability, linearity, and time invariance, given an input-output definition of a system. This video is for the subproperty memory. Here's the definition of memory. A system is memoryless if at each time t, the output value y of t at time t is only a function of the input value x of t at the same time t. Again, our output is y of t, our input is x of t. We're looking to see that they have the same time arguments. In discrete time, the definition is very similar. Now we've replaced our variable t with n and our round parentheses with square brackets. Otherwise, it's the same definition. Example 1. Here's your first example of a mathematically defined system. Y of t equals 2x of t. We talked about this being for an input-output definition of a system, and notice here we see the input, and here we see the output. So this is how we give an input-output definition of a system. Is this a discrete or continuous definition of a system? Because our variable is t, we know this is for continuous time. Now let's go back to the definition of memory. A system is memoryless if at each time t, the output value, y of t, at time t is only a function of the input value, x of t, at the same time t. So let's consider a time t is 1. We substitute that value in for both places. Y of 1 is 2x of 1. It's occurring at the same time here as it's occurring here. So can we say we now have a proof that this is memoryless? No, because we have to do it for every time t, for all times t. So we could try another t. It works for this one too. We've now shown 2 cases where the output occurs at the same time input. We can do it for a negative time t. It works there too. But still, I've only done 3 examples. To prove something true, it has to hold for all t. And going through case by examples is not practical to get to all time t. So instead, we're going to go back and look at the original definition and see that this variable is the same as this variable, and therefore our output will be occurring at the same time t as our input. We can now state this system is memoryless. Alternatively, we can state this system does not have memory. These are 2 ways of saying the same thing. Either notation is acceptable. In this course, to get credit, you must show your work. For this sort of problem, remember, you need to provide at least a sentence describing that you were looking at the 2 time arguments. You can use arrows and point to these 2 variables and say, look, they're the same. You can say t equals t. Do something, but make sure to tie it into this example, and do not just restate the definition. You need to state how it applies to the specific problem given. Here is an acceptable part. The input signal time argument is t, which is the same as the output signal's time argument. And again, include reference to this equation. Example 2. Another mathematical input-output definition of a system. Is this system memoryless? The system is not memoryless. This system has memory. If we consider time t as 1, here our output y at time 1 is going to be 2x at time 0. Because this time does not match this time, we know it has memory. You can use this as an example to use as your reasoning, showing your work. Or you can say that t is not equal to t minus 1. Here, to disprove your answer, one example is allowed to do a disproof, whereas one example, or even any finite number of examples, are not adequate to show a positive proof. Example 3. Y of t is 2x of t plus 1. Let's think about this. At time t is 1, y of 1 is 2x of 2. Because our input and our output are not occurring at the same time, this system is not memoryless. This system has memory. In your work, the input signal's time argument is t plus 1, which is different than the output signal's time argument of t. T plus 1 is not equal to t. Again, one example may be used for a disproof. Let's take the word memoryless as it applies to humans. This often confuses students. What does memory mean if we talk about, oh, my grandfather has lost his memory? Or if I were to say, I don't remember where I put those keys. I have such a bad memory. For humans, we think of memory as only being for an event where the time is in the past, or less than the current time. This constraint is not present when we talk about memory in a signals and systems sense. The future is still memory. Don't let that bother you. We care about the mathematical definition and not just the human definition or use of the term. Example 4. Is this a discrete or continuous system? We see the letter is n, so we know this is a discrete system. Therefore, we need this definition of memory. Does the system have memory? Let's again go through an example to help you think about the math. Consider time n equals 1. Notice how we have this 1 replacing our n on the right side. This summation can be written out as y of 1 is from negative infinity, negative x of negative infinity plus x of negative infinity plus 1 plus x of negative 2 plus x of negative 1 plus x of 0 plus x of 1. We're going to end when our k value is equal to n, in this case, when our k value is equal to 1. Go back and review your algebra to make sure you understand how this line is equal to this line. So does this system have memory? At this particular time, does the output depend on the input only at the same time or at alternate times? Our output time is 1, but what are our input times? We've got lots of different input times, and only one of them is the same. All these others are different. Therefore, this system is not memoryless. This system does have memory. An answer could be that the input signal's time argument is negative infinity plus 1, negative 2, negative 1, 0, and 1, which are different than the output signal's time arguments. Again, why can you here use an example as part of your answer? Because an example can be used to disprove something, but not used to prove something. Because a positive proof has to hold for all time, and that's just way too many examples.